Hey, what's up? It's Monas here. I'm not really sure what I'm going to be posting on my channel, but for starters, this video is going to be about my submission for the Apple WWDC Scholarship that I won about a year ago. Even though I wrote the submission in Swift, which is Apple's programming language they use for creating iOS apps, the idea for this project came to me about 3 to 4 months before I even decided to apply, and it was written with HTML, JavaScript, and CSS. In the description, I'm going to leave a link where you can play around with the simulation that I'll be creating in this video. I'll also leave a link to the code so you can check it out if you want. Before we go into any code, I want to talk about what the project is actually about. So around the time that I was making this, I had really gotten into machine learning and artificial intelligence. For those who don't know the difference, artificial intelligence is kind of a broad term for machines carrying out orders in a smart way. Machine learning is like a branch of artificial intelligence where we give computers a bunch of data and expect them to come up with a good solution to a problem. Of course, we give them some boundaries, but that's pretty much the basics. Anyway, I'd been interested in AI for a while, but basically only managed to do stuff using TensorFlow, OpenCV, and Apple's core AI libraries. These might all seem impressive, but anyone with basic to intermediate programming knowledge can use them really easily. They do most of the AI stuff for you. For example, I used TensorFlow once to create a program that takes in a bunch of tweets and generates new ones in the style of the original tweets. This was only like 20 lines of code. You can use OpenCV for stuff like image recognition. Another project I did in Python was a drawing program where you could draw with your finger in the air, and using my laptop's camera, the program could figure out where your fingertip was and draw that on the screen. Apple's AI libraries are insane, as they make it super easy to create augmented reality applications. Augmented reality, or AR, is like what Pokemon Go uses to put Pokemon in the real world. Anyway, I'd used a lot of these libraries, but I never really understood the concepts behind them. I would feel cool knowing I could program AIs, but I didn't really know what was going on under the hood. One day, when I was going down an internet rabbit hole, I found a Wikipedia page about something called a genetic algorithm. I've never come across a machine learning concept that's easier to learn than this one. Anyone with a basic knowledge of evolution can pick up how it works really easily. Today, we're going to create a simulation of the genetic algorithm at work. In our case, it's going to involve a circle that needs to get around an obstacle in order to reach its goal. It has no knowledge of how to do this to start out, except that it knows it can move up, down, left, or right. So here's how the genetic algorithm actually works. Let's create a species called Circle. All species have goals in their lives that they want to complete. Birds, for example, need to grow up, eat food, drink water, and survive. My goal in life is to be good at least one video game. But the circles have it easy. Their only goal is to go from their starting point to the end goal. But there's a catch. If they touch the obstacle in the middle, they'll die. So they need to find a way as a collective species to learn how to go around the obstacle until the goal. Also, hopefully you've heard about natural selection, where the unsuited members of the species die out. The most fit members of the species live and continue to produce offspring so that the future generations will have less bad genes. We're going to do something similar, but I'll get to that in a second. First, we have to create a population of 100 circles. They don't have a lifetime in terms of time, but they have a lifetime in terms of moves. Basically, they can only move 50 times before they die, unless they touch the obstacle. Then they die instantly. This prevents them from moving way off screen, and it also provides an endpoint where we can kill off a generation and start a fresh new one. During the first generation of circles, all of their movements are completely random. They don't have any parents to look up to, so they have no idea how to get to the goal. they're just going to move randomly until they inevitably die. Next, after all the remaining living circles have met their lifetime of 50 moves, we need to figure out which one is the most fit. This will be the parent for the next generation. Usually, in a genetic algorithm, you have two parents that combine their genes in the hopes of creating an even better child, just like how so many species reproduce. But since our problem is so simple, I'm just going to stick to one parent. The genes of the children will just be a list of all the movements of their parent. Now the last step is mutation. If we just get the genes of the kids the same, they would literally just be clones of their parent, and the circle species would never progress any further than they already have. But our circles are bad boys and they like to rebel against their parents. Every single time they move, the children have a 1 in 15 chance to make a different move than their parent, and that's every single child in the population. For example, they can follow all of their parents' footsteps up until the last one, or they can follow none of them. Both of these are highly unlikely, but the fact that they change slightly means that there's a chance that one person in the species can move closer and closer to the goal every generation. This is what ends up happening, and over time, the species moves closer and closer to touching the goal. After these mutated children get old and live to 50, we're going to repeat step 2 and 3 forever until they hit the goal. We figure out which is the best one, make sure it gives birth to 100 new circles, and then kill it along with the rest of its brothers and sisters. Now, let's code it. First, I'm going to create the HTML file that will display all of the elements on the screen. This is pretty simple because we're not going to add any of the actual simulation elements like the goal or the obstacle in HTML. I'm using the D3 JavaScript library for this because it's really good for creating and manipulating elements. One thing I will add is a menu for changing the population size. This will make it easy to test out various population sizes later. This is going to look really bad aesthetically, but it's 3 in the morning and I really don't care. Alright, so the first thing I'm going to do is instantiate all of the variables and create an initialize function. This is just going to create the obstacle and the goal and make it so that the slider will change the population size variable as well. Then, we're going to add all of the circles. It may just look like one circle, but you have to remember that there are actually 100 circles layered on top of one another. They all start in the same position. Keep this in mind when we run the simulation because sometimes it can just look like a giant blob. The last thing we need to do is create the loop to move the circles a certain number of times, as well as make sure that they die if they touch the obstacle. You can tell they died because they will stop moving completely and just remain still on the obstacle. Also, I'm going to add the part where it detects if the circle has completely touched the goal. Now all we have to do is just let the simulation run. At the end of each generation, you'll be able to see the best fit circle because it'll be highlighted in purple. The rest of the video is just going to be the simulation, but you can check out my other video about the WWDC submission if you want to see how I changed it using Swift. Thanks for watching.